So, let us go on to the next figure of merit. So, the next before going to the actual figure of merit, what I will do is we need some quantities here, that is current rating of transformer. Now, since any transformer winding is dependent on the current that flows, the RMS value. So, we are essentially trying to find the RMS value. Now, you would have noted that any transformer winding is connected in series with thyristor valve. So, current rating of a transformer or a valve are one and the same. So, take any one transformer winding. What is the current rating of the transformer winding or valve? They are connected in series, so the same current flows. Okay. So, for that we will just go back to the circuit. Say the circuit is like this. I have 1, 1, many commutation groups connected in series, 2, 1 and so on, S, 1. 1, 2, 2, 2 and so on up to S, 2. So, we have many such parallel paths. 1, R connected in series with 2, R and so on connected in series with S, R. And all these parallel paths have two terminals, they are brought out. So, the voltage which appears here is Vd, the instantaneous voltage. Now, I make one assumption here. On the DC side, I assume that there is a, say, a large filter, current filter. Say an inductor can actually act as a current filter. So, due to which, for the sake of simplicity, I can represent the DC side current as a constant current Id. So, Id is constant, that is an assumption, and it is justified if I use a current filter, for example, an inductor on the DC side. So, with this assumption of a constant current on the DC side, if I want the current rating of a transformer, so how do I get the current rating of a transformer? So, any transformer winding. So, current rating of any transformer winding or any valve connected in series with the transformer winding. So, for that I have to look at the current in the individual parallel paths. Yeah, if you look at any parallel path, in any of these, what is the current? Id by R. Id by R. By symmetry, all the currents are equal. Okay. Now, the question is, the same Id by R flows through, if I take any parallel path, or same Id by R flows through all the commutation groups. There are S number of commutation groups in any parallel path. Now, in each commutation groups there are Q paths. Now, what is the current in each of these paths? That is the current I am looking at. So, I want the current rating of the transformer winding which is in each of these Q paths. So, what is the shape of the current? Suppose I is the instantaneous current through a transformer winding. Or a valve, of course, because they are connected in series. Okay. So, it is the instantaneous current. So, how is this waveform of I as a function of omega ot? So, I want the waveform of I as a function of omega ot. Say I know that the current through the basic commutation group is constant Id by R. Since Id is constant, Id by R is also constant. But what is the current through any one transformer winding or any one valve? If are you saying I is constant? Now go back to the working of the basic commutation group. At any instant only one transformer winding or one valve is conducting, and all the transformers and all the valves get a chance to conduct. Are you saying all will conduct all the time? At any instant only one conducts, and all will conduct, all will get a chance to conduct. So that will rule out the possibility of constant I. If only one conducts, then for that particular transformer winding it is constant, which is non-zero, and for others it is 0. No, that should not happen. At any instant one conducts and all will get an equal opportunity to conduct. So what is the waveform? It is a pulse. So it is a non-zero value. If I take, say, any cycle of the AC side voltage, suppose I can find a C, any arbitrary some C and C plus 2 pi, this is one cycle. I can always find a C such that between these two instants there is a waveform for I which is like a pulse of value. So it is 0 everywhere except for a certain duration at which it is. So there is a certain duration for which it is non-zero, otherwise it is 0. So this is 0. This is 0. So it is non-zero for a certain duration, and it is non-zero means what is the value? ID by R. See, this ID by R which is shown in any parallel path will flow through the basic commutation group. If you take any individual path in the basic commutation group, the current is still ID by R, because only one thyristor conducts at any time, only one thyristor valve conducts. But what is the duration for which the current is non-zero? 2 pi by q. So there are q such parallel paths. So it is 2 pi by q. So this is the waveform of the current through any transformer winding or any valve. Now the question is, if I want current rating, how to get current rating from this? I just mentioned that by current rating, what do we mean? RMS value. So I have to get the RMS value of this. So we denote the current rating of transformer or a valve by the notation IV, V for valve, V for valve. Okay. So it is the RMS value of the current through the transformer winding or valve. So IV is RMS value, root mean square value. So I have to take the square root of the mean. So there is a period 2 pi, and I have to take the average of the arithmetic mean of the square of the current. So it is ID by R square d omega t, and I have to just integrate this between any two limits which differ by 2 pi by q. So say 0 2 pi by q. Okay. So that is all I have to do to get the RMS. So this gives the RMS value as ID by R root q. So this is the current rating of the transformer or valve. Now, but I mean I just wrote valve in bracket just to mean that the valve rating, the valve current rating and transformer current rating are same. But what we are interested now is in the rating of the transformer. So when you just say rating, what I mean is the volt ampere rating of the transformer. So using this current rating, we will come to what is known as the volt ampere rating of the transformer. So it is simply called transformer rating. So what I mean here is the total transformer rating. Say how many transformers or windings are there? How many transformer windings are there? In each commutation group you have Q, that is multiplied by S, that is multiplied by R. So it is Q into R into S. So many transformer windings we have. So what is the total transformer rating? See, when I say transformer rating, what I mean the total transformer rating. So let me give a notation for this S. S is the usual symbol which is used for volt ampere, the apparent power. Okay. So what is this transformer rating I mean, how is it defined? How do you define the transformer rating? Sorry? Yeah, it is the product of RMS voltage and RMS current. Okay. So, I take the total transformer rating. So, I said it is Q into R into S, which is nothing but the pulse number P. Q into R into S is P. Then I mean the lowercase p stands for Q into R into S. So, P is the total number of transformer windings, and the rating of each transformer winding is the RMS voltage into RMS current. What is RMS voltage? In terms of notations that we have already used. See, we have used the notation EM. So, can I get RMS value in terms of EM? So, it is sinusoidal. Please note, voltage is sinusoidal there. The AC voltage is sinusoidal. So, the RMS value is EM by root 2 into the RMS current. Just now we gave a notation for this IV. So, you can just substitute the expression for IV. Now, what we will do here is, we will also try to get this expression for EM in terms of VDO. Say, just recall, we derived an expression for VDO. What is VDO? VDO is SQEM by pi sin pi by Q. VDO is the maximum average DC voltage. So, we will try to substitute the expression for EM using this equation. So, this gives EM is equal to pi VDO divided by SQ sin pi by Q, and we just now derived the expression for IV, ID by R root Q. So, substitute the expression for EM and the expression for IV in the expression for S. So, that gives the expression for S as, after simplification. So, we will not get the expression in terms of EM anymore, we will get it in terms of VDO, of course. So, it is pi VDO ID divided by, so you can just verify, it is easy to verify that it is equal to pi VDO ID divided by under root 2 Q sin pi by Q. Of course, I have used the equation P equal to QRS, that is why P is not coming here. So, the P is replaced by QRS and there will be some cancellation. So, this is the expression that I get for S, pi VDO ID by under root 2 Q sin pi by Q. It is easy to verify, you can do that. Now, using this, we define one more figure of merit. See, we already defined one figure of merit, value utilization factor. The other figure of merit is transformer utilization factor. So, this is abbreviated as TUF. So, the definition is like this. So, the definition of TUF is the ratio of S to VDO ID. Now, we just know what is S. S is the transformer rating. What is VDO ID? I mean, why I have taken the product VDO ID, product of VDO? Huh? Yeah, it is the power of the maximum power of the converter. Say, if ID is constant, VDO corresponds to the maximum average DC voltage. So, the maximum power of the converter is coming in the denominator VDO ID. Now, for a given maximum power, should I mean, what is desirable? To have as low a value of S as possible or as high a value of S as possible? As low. I mean, I want to see that I invest as low as possible on the transformer. So, this should be maximized or minimized? Minimized. Yeah, again there is a possible confusion here, because when I say transformer utilization should be maximized, the utilization factor itself is so defined that it should be minimized. I mean one could have avoided this confusion by taking the reciprocal of this. Instead of taking S by VDO ID, I could have taken the other way, but I do not want to deviate from what is given in the standard references. So, I am just following what is already done by others. Okay. So, because otherwise when you read you may get a confusion. So, there are two figures of merit which need to be considered. Yeah, if you look at this figure of merit, it depends only on what? I didn't do the substitution. Can you do the substitution and quickly say what is the expression for TUF? So, you can just substitute for S. See, S is in terms of video, so that video gets cancelled with the video in the denominator and ID gets cancelled. So, it is just pi by under root 2q sine pi by q. So, you see that it depends only on q. Okay. So, we will use these two factors, value utilization factor and transformer utilization factor, to arrive at a suitable set of values for q, r and s for a given value of p. Okay. So, we will continue with this in the next class. So, I will stop here.